Hey all, this is Mark with Omni Embedded. This video discusses the use of a PID controller to regulate the speed of a motor. So the parts that we're going to use for this demo are listed on this slide. There's going to be a motor, which is a robotics motor. You can buy this online. There's also an H-bridge. Actually, it's two half H-bridges on one IC. This board plugs into the Freedom K64 board. Then there's also an encoder kit. This is a Hall effect receiver and a small disc with eight magnetized areas on it. So H-bridge, motor, Freedom board, Hall effect sensor, and some minor circuitry that we'll see on the next slide. So this is our stack layout with hardware at the bottom and then software as we work our way to the top. The driver board plugs into the K64. We have a power supply that's going to supply the motor. There's the H-bridge or half H-bridge wired out to the motor. And that's going to be driven by a PWM module, software module, that's driven by a timer section in the micro. Direction for the motor comes from a digital output down to the half H-bridge. And that's going to be driven by the DDC tool in this demo. The sensor is wired to 3.3 volts on the Freedom board and ground, and then it has a 1K pull-up for its signal. And that's mounted on the motor, and it comes in through an input capture, and again through the timer to become RPM feedback. So we have PWM drive, RPM feedback, and direction. The DDC tool is going to provide set point. This slide shows the Vtrex software components that we're going to use. The first is a slew rate generator. We're going to use that to control the rate of change of the set point. Then, of course, the PID controller, proportional, integral, differential controller for closed loop control. We're going to use a glitch filter rather than a low pass filter to filter out high slew rate noise without the filter lag. Measure RPM is going to transfer frequency measurement. This is coming in from the Hall effect sensor. It'll transfer that to RPM, and it also provides predictive spin down. We'll talk about that in a moment. And then the maturity counter is used for stall detection. The Slew Generator is here to help you create a controlled rate of change for a signal that you're creating in software. It's a C++ template class. It has a start value, an end value, and an increment value. And so the first option is to call start with those values, with passing in those values, start, end, and increment. And then call next each time through your thread, and next will return the next increment value until you hit the end of the transition, and then the next call will return a value that tells you you've reached the end. Continuous slew is an easier one to use. You just call it every time through your thread with the set point that you want to hit, and it'll automatically return the value that's the next increment value. The PID utility is used for closed loop control, where you have a plant model and a data set of configurable parameters that's used in the PID calculation. It has on-the-fly parameter updates, clamps for all terms in the output, deadband setting for the I term. It has an optional clamp for the integral history term, so you can avoid integral windup. It compensates for OS jitter automatically. It has a method to transition from open to closed loop seamlessly. And there's a debug option that reveals internal PID data to the DDC through data items. The glitch filter is intended to ignore spikes, glitches, fast transitions that are actually from an incoming data stream. They're faster than physically possible, so you should ignore them. They're probably due to noise occurrences through wiring crosstalk or plant noise. And a glitch filter doesn't give you any signal lag like a low-pass filter would. You configure the filter by giving it a maximum rate of change. So if the incoming data changes faster than that, the data is ignored. The Measure RPM utility has a transfer function that transfers frequency to RPM. You give it the coefficient when you instantiate the class. It also has an anticipatory response for spin down conditions when the separation of the edges of the incoming signal are larger than the sample rate. So in this diagram you can see if we update our calculation for frequency on every rising edge and we're spinning down, you can see that the distance between edges becomes larger than the sample rate. And so in this case, every time we have a sample or a call for a new sample, the function calculates the new RPM, assuming that there was a edge right there at the sample rate or the sample call. So if there hasn't been an edge since the last sample call, it assumes that there's one right there. That gives us finer granularity in our RPM calculations. So the maturity counter class is meant to determine when a condition has been there long enough to call it real. It's a C++ template class, and whenever you pass in a true, the counter is incremented, and if you pass in a false, the counter is decremented down to 0. The increment values are user-defined, and there's also a counter threshold and a max count clamp. And so what happens is, as we're counting up from 0, if you're passing in true, meaning that some condition has become true, we count up until we hit the threshold, and the maturity counter returns false until we hit the threshold. And so that indicates that the condition has been present long enough that we're going to assume it's a valid condition. And as long as you're passing in true, it'll keep counting up until it hits the max or the clamp, and then it'll clamp at that point. And then if the condition disappears, we'll begin, as you call the counter and pass in a false, meaning the condition is no longer there, it's going to decrement until it crosses the threshold. And during that time, it's going to return a true, meaning the condition is still here. And then when it crosses the threshold, it'll start returning a false, meaning that we've dematured. Since the user can define the increment and decrement values, you can use that to either center bias, true bias, or false bias the counter. So it's the data center that ties everything together, and this is a list of data items or variables for this demo. Everything with an SNGL_PID is here for tuning. These would go away for production. The rest of the variables will be used to control and view through the DDC tool. So let's take a look now at the feature code, the two files that implement the PID and the motor control. We've got the header file on the left, the CPP file on the right, and this is a location in the project. You can actually pull this project in onto your local drive and create a workspace and open and build it. So the Vtrek components that we're utilizing are the RTOS adapters, and then we discussed the Slew Rate Generator, PID control, glitch filter, measure RPM, and maturity counter. This is a singleton class, and the constants that we have are, number one, the number of configurations, PID configurations. So this is set up in this solution as a windowed PID. So we have an array, the PID config data array, and within that we can create and add PID tuning parameters. And in a lot of cases, you'll need to switch into, pull in and out different parameters depending on what the system is doing or where it's at in its range of operation. And so I kind of start off setting up a solution with this in mind. And if I don't need it, then no issue having it. But in this case, the indices are these two constants. So there's a low-speed PID operation and high-speed PID operation. It turned out in the case of this solution that I'm only using one of these two, the high-speed. But there's quite a bit of additional tuning that can be done in this system, and there's a low-speed element in the array that could be used, and then it's just a matter of determining where you're at in your RPM range and then switching your index or pointer into the tuning parameters that fit that range. Max RPM was determined by, it was empirical. We measured it. The stall maturity count, this is for a condition where we're pumping power into the motor, but the RPM isn't keeping up with what we're putting in it, or the RPM is staying at 0. And at some point, you've got to realize that you're stalled and kill power to the motor. And that's what this maturity count is about. The glitch sample count is set to 10. This is for the glitch filter. And the percent per pass is set to 10%. Now that is any deltas from one RPM measurement to the next that exceeds 10% of range would be considered a glitch. The slew percent per pass is 0.75, and so this is for the input set point. If the set point is adjusted faster than that, then the slew generator is going to cause the rate of change for the set point to be no more than 0.75 per pass through the thread function. The transfer slope for the RPM, this is transferring from frequency to RPM, is 7.5. We're running the task at 10 milliseconds, or we're running from the 10 millisecond task. So our thread function is running at 10 milliseconds. And this is also part of stall detection. If we don't reach our set point within 0.9, if we don't get to within 0.9% of our set point, then we're going to call it a stall. Should also mention that there's a symbol definition up here that's for the tuning variables and tuning members. You'll see how that's used, like right here. We're conditionally compiling variables that are used for tuning. So if we go through the list of private members, this is a data item which can output motor RPM, motor PWM, motor power essentially, and this is what goes through the timer channel and creates a PWM signal for the motor. So it's motor power. Here's our thread. We're going to run off the 10 millisecond task, and so this is a periodic thread. Our PID controller, the glitch filter, RPM slew generator, and here's a pointer to our PID configuration data. So those would be the term coefficients and so forth, the clamp values. Previous set point, now we're going to write out our RPM. So call on the measure RPM function, we take the return value and put it into a data item so that we view it. This is our configuration array, maturity counter, stall flag so that we can watch for the motor stall fault. And then this is the slewed set point. So this would be the set point through the slew rate generator and the output of the slew rate generator. Now these are variables. This shadow data is a structure of data that is populated by the PID, and then we push that data out into data items so that we can view them through the DDC tool and watch them as we tune. Looking on the CPP side, here's our constructor. Our resources are constructed here and member variables are initialized. Here's where we are loading up our PID configuration data, and you can see the various values that's in this data structure. So we've got the gain coefficients, output gain coefficient, mins and maxes, I-term deadband, then output mins and maxes. Right now, we're only using this element, the low speed. In fact, that's where we've loaded our pointer right here, is with the low speed, a pointer to the low speed element in this array. And the data that's put in the high speed is just bogus data, so it's there to be used. If you decide to put this on your laptop and play with it, you're welcome to add elements to this array and fine-tune the motor operation. Right now it's loosely tuned. Here's our conditionally compiled variables. So we're instantiating the controller, and we're getting write interfaces for the terms that we're going to push out for viewing. Here's where we start the PID controller. We clamp the integral history and then start it. And we're starting our Slew Generator. And then we're getting write interfaces for the RPM and fault data items. If we get into the thread, so we're going to run through this every 10 milliseconds, and as we come in, we read the current RPM from the RPM feedback object. So when we instantiated this object, measure RPM, we gave it a data item that is populated by the timer. It's the input capture channel, essentially. So the frequency of the input capture, the frequency of the Hall effect sensor is pushed into this variable, and then measure RPM uses that to convert it to from frequency to RPM. So it's just a simple call as we go through this thread to find out what the current RPM is. Then we calculate that in terms of percent of full RPM. Now in the feedback and set point, we're using percent of full scale. So by using that, scales both the input and feedback to the same scaling. And when this is enabled, we're going to read the bypass glitch Boolean that we're controlling through the DDC tool to find out whether or not we should apply the glitch filter. And then we push out our current RPM. Now we're going to read the set point that also is being controlled in this case by our DDC tool. And then we also, if tuning's enabled, we look at whether we should bypass the slew rate generator or not. And if not, then we'll make our call to the slew rate generator and then output the slewed set point. And here's where we check for the fault, the stall fault. So if our percent of set point, the ratio between the percent full RPM and our set point is less than 90%, then we're going to set the fault. The maturity counter was set to 200 right here. And so this state has to be true for 2 seconds in order for us to set the fault. Once we set the fault, we shut down motor drive, and we don't clear the fault until the set point has been set to 0. Here's where we're reading in coefficients from the DDC tool. We're setting the PID counter to open loop or not, depending on what we're setting this to through the DDC tool. And then finally, we're calling the PID controller. If we're not in fault state, we take the output of the PID and push that out as motor power. And if we're tuning, we also take the shadow copy of the PID terms and push those out so that we can view them through the tool. Okay, now that we've walked through the code, let's watch this thing in action. We have the code loaded on a system, on a platform. So there's the K64, the H-bridge, and the motor board set up on a quick and dirty load system so that we can apply a load to the motor. Open this in the DDC tool. You'll see what it's doing now is it's uploading the data dictionary. That's all of these variables. These are the variables that you see in the data item configuration file. And I have already created a view for motor tuning, so let's pull that up. Now, how do you create these views? Well, these buttons at the bottom, there's a create controls and a create chart. Create controls is creating a palette like this where you can throw in data items that are overridden so you can control them from here. Once you've opened one of these, you'll be asked to give it a title, and then you can drag and drop the data items into it. For Booleans, you'll get this type of control and you have the ability to set the labels if you want to change it from off and on to something else. For analog controls, you can set the range and scaling. So, here's the minimum and maximum values, and then the slope and offset for linear scaling. In this case, we have the coefficients, the term coefficients. So there's the P, the I, and the D coefficients, and then we've also got the set point. These are the switches that we put in for running either open loop or bypassing slews so that we can test that part. This is a chart. So to create this, we use the Create Chart button and give it a name and then drag and drop signals into it. So these are reading and charting data items. In this case, we have the set point, which is this guy, the PWM drive, which is the amount of power that we're driving the motor with from 0 to 100%. The motor PWM feedback in percentage 0 to 100. And then the slewed set point, so that's taking this and running it through the slew generator, and this is the output of the slew generator. On this chart, we have the P term, the D term, and error. These are coming from the PID. These are the internal terms that are calculated. Then in this chart, we have the I term and the integral history term. You'll notice up here, we're showing the stall fault. So let's run the motor and see what we see. If you look over on the picture, you'll see that we're definitely turning. Looking at the motor RPM feedback and the set point, they're right together. This is power going into the motor, and then this is the slewed set point. So if we watch what happens when we give it a step function, we can watch the green and pink colored signals. And I'll pause this. You can see that the green was a step function. And the slewed signal ramped up at a slower rate. And so now I want to show you what happens if we don't have that slew function in there. I'm going to go from 0, I'm going to go to 0 and then enable this slew bypass and turn it on. And then I'm going to go to 70%. We should be able to see what I'm talking about. In this case, power went up to 100%, so it hit the ceiling. We didn't have any headroom left, and that was when we went from 0 to 70%. So for a short period of time, we were maxed out, and we really didn't have any control over what happens during this ramp up. And if you do the same thing then with the slew rate on, we'll see that doesn't happen because we're coming up at a slower rate. So that's one of the things you want with a control system is when you're spooling up or spooling down, you need to have still enough control to be able to, when you need to stay closed loop. Otherwise, you'd have a system that's essentially running open loop for a short period of time. I also want to show, I'll bring this down to, let's say, 40%. And we'll see what happens if we bypass, if we go open loop. And now I'm going to increase the load on the motor. You can see what happens. We don't have any speed control and fall down to 0 and stall. So now I'll go closed loop. There we are up at 40, and now we'll see what kind of speed control that we have. As I increase the load on this, we see that the speed stays pretty much the same. power to the motor is going up as I increase the load. And then as I release the load, power goes down. You see a little bit of overshoot there. So there's room for improvement on this PID controller in terms of tuning. So over here we're seeing what's happening inside of the PID. So that the P and D terms, you can see some ripple essentially. And if you're hearing the motor, you'll note that the gearbox on this particular motor isn't the best. And much of what you're seeing there, I think, is gear noise. And then in this I-term chart, we're showing both the integral history and the I-term. So if we turn the history off, you're seeing that the I-term is fairly flat, but it does respond when I load it. And it's right at set point. So another feature I'd like to demonstrate on the DDC, so you can see in this case how easy it would be to create different conditions and adjust tuning and test the algorithm. I'm going to open playback, open a CSV file that's already been created, which is motor playback, and I want to show you what that file looks like. It's just a simple CSV file. So CSV file, this one just has one column. In row 1, this has the name of one of the data items. It's the set point. And it has an S colon. S stands for stimulus. So this tells the playback feature that we're going to hijack this signal and inject these data values. An R colon means response. So that would mean that we're going to read back any variables in columns that are listed as R colon meaning response. Now in this case, we're just going from 30 up to 77 and then back down to 30. Pretty straightforward. And I'm going to say continuous playback mode, which means that when it hits the end of the list, it'll go back and restart it. And then we'll start playback. And it just told me that it can't because someone else has it hijacked. So I'll release it there and then start it here. And you can see that it's playing back that data. We can control the playback time as well. So if I set this to 100 milliseconds, you see that we're taking twice as long to go through the loop. So if you want to exercise a system and collect data, this is a pretty straightforward way to do it. On any of these charts, you've got the ability to save data to file or to log data. You can also, within the playback service, you can subscribe to variables and log those away as well through the log file. The last thing I want to mention while we have this tool open, well, there's systrace, so we'll have a look at that. We have a number of messages flying through here. You can log those as well. These are messages, they're just debug messages that you can print from code. You can also set text filters to filter out what you don't want to see in here. And while we're here, we'll just go take a look at the Rti Stats. And we're on the 10 millisecond thread, or task. Here's the 200 millisecond. Let's get up to and find our 10 millisecond. All right, there's 10 milliseconds. So looks like we're using 30% of the stack. Periodic rate is 9.948. That's pretty close. What else is interesting in here? Our CPU utilization is under 5%. We're not doing much work with this loop. And then if we scroll to the bottom, our overall utilization is 10%. So if I stop playback and then go over here and re-hijack it and set it to 0, just be interesting to see if that changes our utilization. What we see, we're in the background task most of the time now, but what we see is that we really didn't see any change in CPU utilization with the motor on or off, which kind of makes sense because within that loop, within that thread function, we're pretty much still doing all the same steps that we were with the motor running, which is really a good practice if you want to keep your CPU load even and more predictable. Then that's kind of the way you should design things, is that we don't really change what we're doing based on whether something's operating or not. Okay, so to conclude the presentation, we've seen closed-loop motor control, speed control in this case, a solution that's compact and short. Minimal time was required to code it. The reason is that we mostly used support through the utilities and code that's already available in Vtrek. And then tuning the control through the DDC tool was quick and easy, and of course exercising it and testing it through that tool would have been fairly easy as well. I might add with the DDC tool that it's based on a DLL. What you just saw as far as the application are just the presentation part that's utilizing the DDC DLL, and that's a .NET DLL, and you can import that to many languages if they're .NET compliant. And so you can create your own test platform using the DDC bottom end and create testing and exercise your product just as easily that way. Well, thanks for watching, and please give us a visit at omniembedded.com.